Hello. Today we'll look at trigonometric interpolation, and the idea is that this will lead us into something called the discrete Fourier transform, and then we'll look at an algorithm to compute the discrete Fourier transform. The algorithm is called the Fast Fourier Transform, or FFT. So let's try to understand trigonometric interpolation first. So for some positive integer, we'll let t sub n, capital T sub n, be the set of all trigonometric polynomials of this form. So that a trigonometric polynomial just means we have we have real valued coefficients in front of sines and cosines at different integer valued frequencies. Well, I guess integer valued wave numbers. Okay. Of course, there are many generalizations of this. You might wonder why it's called a polynomial in this case, because with the trig functions, this doesn't necessarily look like a polynomial. But by Euler's identity, we can write something like we can write cosine is e to the ikt plus e to the minus ikt divided by 2. And then I can write this as something like 1/2 times e to the it to the k plus 1/2 e to the minus it to the k. And so expanding out everything in this form, we see that we are getting polynomials here where we are evaluating at the point e to the it. Okay, so and similarly for sine kt, of course this is just as a reminder, it's e to the kt minus e to the minus ikt over 2i, and we have a similar expansion there. Great, so this is what's called real trigonometric interpolation, using the real coefficients in front of sines and cosines. And I'm just going to state that we can do this. So first of all, what is a trigonometric interpolation? So given some points y0 up through y2n, these are just real numbers, and say 2n plus 1 distinct points on the interval from 0 up to 2 pi, then there exists a unique polynomial p, so, excuse me, let's call it qn in our trigonometric space, such that it interpolates the data. That is, qn at tj, it's equal to yj for all j, going from 0 up through 2n. All right. The proof of this is just to show you a polynomial that works. I'll let you verify the uniqueness and also let you verify that this works on your own. But let's just, so the proof is just a couple lines here in some sense. Qn of t, we'll let this be, let me write it this way. Let's define the Lagrange type trigonometric polynomials in the following way. This is a product. I goes from 0 up to 2n with I not equal to k. Here we'll have sine of t minus ti divided by 2, and all that divided by sine of tk minus ti divided by 2. And the idea is that, so this is a definition of these LK functions, and we'll note that if you plug in, say, tj, that you get either 1 or 0. You get a 1 if k is equal to j, and a 0 if k is not equal to j. So these are nice little functions. Notice, so the only variable here is showing up in the t. So these bottom things are just numbers. And we're taking a nice product of these to get a function which gives us just 1 at the point we want to interpolate and 0 otherwise. The function is not 0 everywhere, but it's 0 at the points that we want to interpolate at. So then let qn of t be a summation, and we just plug in the point. So we just multiply by the points that we want. k goes from 0 up to 2n, like this, right? Then by the above property, Qn at Tj, Tj gives us exactly just our the Yj point back. So one objection might be that these aren't exactly of the form. These aren't looking like they're a form of trigonometric polynomials, but right, they're a product. We have this 1/2 in the middle, but right, so claim these LKs are actually in Tn for I guess T. Yeah, these are in Tn for HK. And to see this, use e.g. trig formulas for such as sine alpha times sine beta, and so on. So there are a number of these product formulas. So you'll be able to expand products of sines out into some sums of sines and cosines, and use this many, many times to get that this is actually a trigonometric polynomial. Okay, I'm not going to go further into that discussion because it takes us away from the main discussion. That is the complex setting. And the complex setting is much nicer. So I just wanted to mention the real setting to say that we can do this, that it's part of trigonometric interpolation. But the idea is that we'll set En, so set En to be e to the I n x. And remember that this is, first of all, it's e to the I x to the n. And also that this is cosine of x plus I sine of x to the n by Euler's formula. And you can actually write this using this piece as cosine nx plus I sine nx, which has a this equality has a nice name. I think it's a de Moivre's formula. But okay, so we'll set En just to be these nth powers of e to the ix. And then we'll let t sub n, this is a t tilde if you want, we're in the complex setting, to be just the span over the complex numbers of e0x up through en minus 1 x, like this on, we'll take these as defined on 0 to 2 pi. And I'm writing open 2 pi on the right, closed on the left, so this includes 0, it does not include 2 pi, because I want everything to have a unique value of x that we're plugging in. Of course, this function, sorry, that's e sub n of x. This function at 2 pi and at 0 is the same by the periodicity of sine and cosine. All right, let's also define some equidistant points. On this interval, 0 to 2 pi, by xj, and sometimes I'll write them as tj, and we'll take 2 pi over n times j, where here j goes from 0 up through n minus 1. Okay, so what's the interpolation problem? So first of all, notice that before we just said, well, we could take any arbitrary points. We are now taking a fixed equidistant set of points here, and that's very crucial for the analysis that comes ahead. We'll always want these to be equidistant points from now on. All right, so then we'll choose, so the interpolation problem is the following. So we'll find, we want to find some polynomial in our T sub n space, such that P of x is equal to the summation of k goes from 0 up to n minus 1, ck e k of x, where these ck's are just complex numbers. Right, so the goal is to find these ck's such that P of 2 pi over nj is equal to f at 2 pi over nj for some given function f. Right. So although I'll talk about this as if we are given a function, because that's often the setting that we're in. We're given a function and then we evaluate at the points, but all we will ever use is the values of the function at these locations. So really, we could just call these things, that is, we don't need to be given a function, we just need to be given a discrete number of points, a finite number of points. Where we want to do this interpolation. So for instance, maybe we could call these just yj's or zj's or something, and be given a bunch of numbers, and we want to shoot a trigonometric polynomial, complex trigonometric polynomial through those points. Okay, great. So rather than try to recreate what we did before with these Lagrange type interpolations, which is not very nice in practice, we have a much nicer way to go here. But to do that, we need a little bit of framework. So we want some L2 1 over 2 pi functions, let's say operations. These are just some operations. So we'll take f comma g to be an inner product, but with a weight is 1 over 2 pi. So it's the inner product f of x, g of x complex conjugate dx. So the usual L2 inner product does not have this weight here, but we'll take it with the weight for some convenience. And the norm, which sometimes I'll just write as double bars or double bars sub L2. This is just 1 over 2 pi times inner product 0 to 2 pi of f of x squared dx, 1/2, like this. All right. So in this case, and remember that L2, this space up here, L2 0 to 2 pi, is just a set of say measurable functions defined on this complex value functions for which this norm is finite. The integral here is technically the Lebesgue integral. We won't worry about those subtleties now. So one of the first things to notice is that if we take the inner product of En with En, then this is just 1 over 2 pi times the integral from 0 to 2 pi of e to the I n x, e to the conjugate of e to the I mx. So conjugate there, but the conjugate of a e to an imaginary number is just e to the negative that same number. So we get something like this. And then this function, right, if n is equal to m, then we just have e to the 0 here. So we integrate from 0 to 2 pi and get 2 pi, then divide by 2 pi, we would get 1 if n is equal to m. If n is not equal to m, then this formula can be computed by usual calculus, right? So we'd have something like e to the I n minus m x, and then divide by I n x, sorry, n minus m x, not x, excuse me, just I n minus m, and evaluate this from 0 to 2 pi, but by the periodicity up here in the complex exponential, that is the periodicity of sine and cosine, those two pieces will agree, so their difference will be 0, and this will just cancel out. Oh, excuse me. So let's just go back there a little bit. So that means that this inner product is just either it's 1 if m is equal to n, then 0 if m is not equal to n. Great. So this is sometimes what's called the Kronecker delta function, which is denoted delta sub nm. Great. Okay, now let's have a few more definitions. This is the discrete inner product. It's a weighted inner product again. And for this, we have what we'll denote. We'll take two functions, f and g, but then I'll denote this with an n. And I guess I'm using, well, maybe we should use round brackets for this thing. It doesn't matter. Take this to be 1 over n times the summation. J goes from 0 up to n minus 1 at f of x sub j, g x sub j, like this, with a conjugate here. And so notice that this is pretty analogous to the above inner product. In fact, you can see it as a Riemann sum of that, Riemann sum approximation of that inner product. But for the current purposes, we'll just denote it like that. Notice it's also not quite an inner product on L2, because if f and g can be non-zero off of the interpolation points, and you can still get something which is 0 out of this. So technically this is maybe some type of pseudo inner product. But it does satisfy, so note, if you take f, I'll just still call it an inner product, f inner product with itself will be greater than or equal to 0, and f inner product, f inner product with g will be, we have the conjugate symmetry property that we're used to from a standard inner product showing up here. We don't have quite positive definiteness, but we have the important other properties such as linearity in the first argument and conjugate linearity in the second argument. Hopefully are pretty obvious. All right, so with this in mind, so we're not too worried about whether or not it's actually an inner product. It's just with this in mind, it can be a nice, with this inner product in hand. It's a nice notation for what we'll use before. That's what I'm trying to say. And it has also the similar property. If we plug the exponential functions that we saw before into this thing, it also is either 1 or 0. That is, it's another Kronecker delta function. So it's 1 if m and n are equal, or it's 0 if they are not. And that's the reason why we are normalizing by this 1 over n. Just to maybe see this kind of quickly why the n arises, imagine plugging those complex exponentials in here. You'll get these two multiplied together and then summed. You're summing over points in the unit circle, and you get cancellation all the way around up to, well, you get a contribution of, if the m and n are not equal, you'll get a cancellation going all the way around the unit circle. If they are equal, then you'll just get this product will be e to the I nx, e to the minus I nx. That's e to the 0, which is 1. So you'll just add up 1 going all the way around the unit circle. We're going from 0 up to n minus 1, so that's n terms. So we get a factor of n. We divide by the factor of n. We divide by 1 over n, and so we just get a 1. So we have the same type of orthogonality property for these basis functions that we had in the continuous case. Okay, we're now set up. We've cut all the vegetables. We're ready to make the soup. So let's see what we can do. So let's denote denote the matrix W by, let's say W is a complex valued n by n matrix with jth row will be E0 at xj up through E sub n minus 1 at xj, like this. So that is, if we set lambda to be the nth root of unity, then that primitive nth root of unity, if you like, then the jk entry of W is just lambda to the jk, like this. Because remember, as we plug these points in to the exponential function, these multipliers j will just come up here into the numerator. Into the exponent. All right. So due to the orthogonality, that is that if you take n em with the discrete inner product, you get delta nm. It follows that W conjugate transpose, you can write W star if you wish, times W. If you think about what this is doing, this is taking all possible inner products between the en and em terms evaluated at these various points. So what you'll get is exactly n times the identity matrix. So that this gives us a quick way to solve. So for the interpolation, you might ask, where does this matrix W arise? If we go back to the trigonometric interpolation problem, I guess that was on the previous page, here, we would like to be able to plug in these evenly spaced points, 2 pi n over j, excuse me, 2 pi j over n. We'd like to be able to plug each of those in, and every time we do, we'll get a long sum of a whole bunch of terms with ck coefficients out in front, evaluated at the various evenly spaced points. So that means that, here we go, that means that the matrix will arise as, so also C, say letting, okay, so let's denote this. So let's denote those coefficients, C by maybe C vector by C0 all the way down through Cn minus 1. Let's let F vector be the points, I'm going to note them F0 down through Fn minus 1, but by that I just mean F evaluated at x0 all the way down through F evaluated at xn minus 1, like that. So then, say interpolation equation, the system formed by plugging in all each of the xj points is a form W times C vector equals F vector, and that's it. So I mean, the first thing we can notice is just by, if we can just invert this matrix, we'll be able to solve for C. But we've seen above that W transpose conjugate times W with matrix multiplication gives us the identity. So we effectively have the inverse sitting right there for us. So if we multiply by W conjugate transpose, we obtain, so we have W conjugate transpose WC equals W conjugate transpose times F. But that implies that this is n times the identity matrix. So just n times C is equal to W conjugate transpose F. And that implies that C is just 1 over n times this transpose. So that's pretty nice. It seems like, this F vector. It seems like this is already a nice result in the sense that we don't need to go searching for a nasty formula for the inverse. It's just sitting right here. And we could call this problem solved. And it is solved from the perspective of forming the DFT. So the map from, if you take F and you send it to C, as defined above, this is called a discrete Fourier transform. Or DFT. So we want to be clear, it's this map that is the transform. In a moment, we'll learn about something called the Fast Fourier Transform. The Fast Fourier Transform is an algorithm used to compute the discrete Fourier Transform. So this often gets kind of blurred a little bit. Sometimes people say they want to compute the FFT. What they mean is they want to compute the DFT using the FFT, using the FFT algorithm to do it. Okay, so let's examine this a little bit further. So let's look to the kth component. That is CK from this map. This is just 1 over n times the summation. J goes from 0 up to n minus 1 of f xj times e k xj conjugate. But this can be written as just the discrete inner product of f with e sub k. So we have a nice formula. So then our interpolating polynomial, is just this sum ck e sub k of x. K goes from 0 up to n minus 1, where ck is given by this formula. Okay. So in that sense, we're done with the trigonometric interpolation. Okay, but let's see how much this costs in terms of computation. So computing the DFT directly, as we just saw. Right? So that means we want C to be equal to 1 over n times W bar transpose times F. Well, the W bar transpose, we could compute this in advance, even times the 1 over n factor. This can all be computed and stored in a computer for future computation, right? So this is just some kind of n by n matrix of complex numbers, but we won't worry about whether things are complex or real for a moment. So the counting for these, right? Counting multiplications. The idea is that multiplications are pretty expensive. At least in the old days, multiplications were much more expensive than addition, although with modern architectures, the gap between the speed of additions and multiplications is closing. But for now, let's just count the multiplications and see how that goes. So if we have, for instance, if n is 2 to the 10th power, which is 1024, so if we have a 1024 by 1024 matrix, then a matrix multiplication, well, we have to multiply every entry of F by the entries of W, and that's n squared multiplications, right? So that's about 10 to the 6th, because this is about 10 cubed. And yeah, so that means that this thing is pretty expensive. If we have something like 2 to the 14, which is 16,384, then when we compute n squared, we get something like 2.7 times 10 to the 8th multiplications. So this is right. So we have about by increasing by a factor of 4 here, we've gone up by a factor. Well, right. It turns out it's a factor of about 16, right? 4 squared. So this means, sorry, what am I saying by a factor of 4? Right, we're scaling like n squared, is what I'm trying to say. If we went up by a factor of 4, we'd go up by a factor of 16. Here we're going up by a factor of 16. And we go, the number of multiplications goes up by a factor of 256. All right, so it's quite expensive to do this for large matrices. However, there's another algorithm, the FFT, which goes about n log base 2 of n, is how many multiplications it takes. And if you take a look at that, plugging this in, this will be about, well, log base 2 of 2 to the 10 is 10, times n is already 2 to the 10, so that's about 1024. So this is about, so that's 10 cubed, this is about 10 to the 4th operations. And down here, scaling up by a factor of 16, you can check this is about 2.3 times 10 to the 5th operations. So not all that much more expensive. This thing scales very nicely. We're doing far fewer computations than, say, 10 to the 8th for this type of operation. So this is what this is the kind of gain that we can get out of the Fast Fourier Transform. So let's talk about the Fast Fourier Transform now. By the way, the Fast Fourier Transform was named some years ago as one of the top 10 algorithms of the 21st century. It really is everywhere. It shows up in myriad applications. In fact, your ear, in some sense, is already, the cochlea in your ear is already doing a Fourier transform just to hear the sound of my voice. My voice is transmitted to you as some type of function, some type of pressure wave, as it's coming out of your speakers or earphones, and it vibrates a membrane in your ear. Those vibrations get translated into frequencies by the cochlea of your ear. It's a little snail shell looking structure inside of your ear. And those signals are sent to your brain as electronic signals or electric signals. So the Fast Fourier Transform, or well, the Fourier Transform, I should say, is kind of, it really is ubiquitous. It can also be used, for instance, to quickly multiply very large numbers together. It's used in a huge number of applications, partial differential equations being a major one, but it really is just sort of a fundamental way to view data differently. So right, this is a one-to-one and onto map from data in sort of physical space to data in frequency space. So in some sense, I mean, by looking at the discrete Fourier transform, we've lost no information. It's just a different way of looking at any set of data. Okay, so let's for this next bit, we have an idea. So this idea has been rediscovered many times. Gauss was probably the first one who discovered it. It was later rediscovered and popularized by Cooley and Tukey, so it's sometimes called the Cooley-Tukey algorithm. The idea is so the following. So first we'll assume that n is equal to 2 times little n. So that is, we'll take an even number of points. And then let p and q be trigonometric polynomials, be trig polynomials of degree less than or equal to n minus 1, such that for our evenly spaced points xj, these are xj 2 pi j over capital N, but remember that's 2 pi j over little over 2 times little n, which is just pi j over n. We will interpolate, say that interpolate, excuse me, having a little, this is a difficult screen to write on, then interpolate as the following. So we'll take p on the even points and interpolate the function value at those points, and q will interpolate at the odd points. So 2j plus 1 is equal to f x 2j plus 1. Here j runs from 0 up through little n minus 1 on both of these. All right, so the idea is to split into even and odd points and look at these sort of interlaced things. So if we have some points here, these are normal interpolation points, which are supposed to look evenly spaced. We'll have, say, q interpolating here, and p will interpolate at the, I guess q will interpolate at the not filled in points, and p would interpolate at the filled in points. It's not immediately obvious that that should help. But let's take a look at this theorem that the trigonometric polynomial capital P of degree 2n minus 1 that interpolates f at x0 through x2 n minus 1 is given by capital P of x is equal to 1 half 1 plus e to the I n x times little p of x plus 1 half 1 minus e to the minus, 1 minus e to I n x times q at a shifted version here, q at x minus pi over n. So that means if we can find these other polynomials, then by just a few multiplications, we can reconstruct the larger polynomial. And this is great news, because what that means is each of these, it costs to interpolate, or to compute p of x. Remember, it costs number of points squared to do that computation. So this is number of points squared to compute this. If we have half the number of points, because we're just doing the even points, that will only cost n squared, n over 2 quantity squared. But that is the same thing as n squared over 4. We get another n squared over 4 operations to compute q, and then at the cost of a few more multiplications, this is roughly the sum of those. That is, we get something like n squared divided by 2 to compute the larger polynomial. So this is what's sometimes called a divide and conquer algorithm. We cut into smaller pieces that can be done easier, and then we push them back together by some operation like this to get the correct operation. So maybe I'll just check one of these. So the theorem is really just to check this. So at the even points, we want to make sure that we're interpolating correctly. So then we have x2j. This is 2 pi times 2j divided by 2n, which is 2 pi j divided by little n. So we have e to the I n x sub 2j. This is e to the I n times 2 pi j divided by little n, but the little n's cancel. And that means that we get, this is e to the 2 pi I times j, but this now is just 1, because e to the 2 pi I is 1, right? That's going all the way around the complex unit circle once, no matter the power j, right? This is just, if you want, it's e to the 2 pi I to the j, so it's 1 to the j, that's 1. And so, if we take a look at p of x2j, this is 1/2 times 1 plus 1, just going from the formula above, p at x2j, but that is just 1 plus 1 over 2 is just 1, so this is p at x2j. But p already interpolates f at the correct point, so this is f at x2j. And so we're done. Check mark. So for the odd points, I'll let you check that as an exercise. Okay, so we can write this in somewhat of an efficient way. So this is sometimes called the coefficient recombination formula. It looks something like this. So the little polynomial p on even points, this is, if we write this as sum j goes from 0 to little n minus 1 of some coefficients alpha j, ej, x, we write q of x, q of x is the same thing but with beta coefficients, beta j, ej, and big P of x is the summation, summation j goes from 0 up to 2n minus 1, gamma j, ej of x, like this. Then we get the following combination, recombination identity. So gamma j is 1/2 alpha j plus 1/2 e to the negative I pi j divided by n times beta j, where j goes from 0, 1 up through n minus 1. And so that's only half of them, right? So that takes half of these guys. And then the rest of them, which I'll write as gamma j plus n. So j will go over the same range. This is 1/2 alpha j minus 1/2, minus 1/2 e to the minus I pi j divided by n times beta j. And again, j goes from 0 up through n minus 1 because we have this little plus n here. In fact, maybe this is worth commenting on just one point here. You might have noticed that we're taking just positive coefficients on these things. And if we go back to the way that we saw trigonometric polynomials before, actually if we go all the way back to the sines and cosines, the sines and cosines, should have some negative exponents in them. But in the discrete case, we get those negative exponents by going all the way up to n minus 1 because there's sort of conjugate symmetry with the wrapping around to the negative pieces there. So that's why we can kind of do these all in tandem. Notice that it's written so that this can be done in a loop. if you just have just by updating both of these coefficients at the same time, you can have a loop from j goes from 0 up to n minus 1. Update these at the same time, and you're good. Let me mention a couple of things, and then we'll talk about operation counts. One thing is that these factors here, that are sometimes called the twiddle factors, can be, I don't know why they're called the twiddle factors, but somebody called them that. These can be computed in advance and stored in memory. And this is sometimes called, we can store in advance. And these are sometimes called wisdom. So that is sometimes in some FFT algorithms, you can run the formula through once and store them using various libraries call these by different names, but you store it as something called wisdom, and then the next time you need them, they're already stored and ready to go. In fact, you could include the 1/2 in that computation as well, but that's another point, that sometimes the 1/2 is not included. Notice it's 4 extra multiplications here, and only a little bit of it could be stored in advance. You could sort these pieces in advance, but then you still have at least 2 multiplications to worry about for the alpha j. I guess 1 for as you're running through the whole gamut of j's. 1 for each gamma j would have an extra multiplication. If you do not include the 1/2 factors, it's okay. What you end up getting is an extra factor of n multiplying your discrete Fourier transform. And most implementations, such as the standard one in NumPy, the standard Fast Fourier Transform in MATLAB, all compute these without the 1/2 factors for speed. And then when you're done, you just have n times the discrete Fourier transform. You can divide by n if you want. You often don't need to divide by the capital N, because sometimes you're just going there, going into Fourier space, and finding the Fourier coefficients, doing some manipulations, and then taking an inverse Fourier transform. If that's what you're doing, you probably don't care about the multiplication by n factor, because that will be taken care of when you take the inverse Fourier transform. However, if you're trying to do something like compute a norm using the Fourier coefficients, and using something like Parseval's formula to compute the norm directly from the Fourier coefficients, then you'll need to divide by n at some point. And you want to be careful at what point you're doing that division, because maybe you should actually, depending on where you're doing it, maybe you want to divide by, n squared or square root of n, depending on your setup. Anyway, so it's always good to check the algorithm that you think you're computing. Another time you might want to do this is if you're actually going to display the Fourier coefficients, like in a plot, then you want to divide by n. Good way to just check this is to compute a Fourier transform with whatever system you're working with say n is equal to a certain number like 64 or 128 or something, some power of 2, and then increase that number. So run it at 64, then run it at 128, and see if you're seeing the same results. If your results are not scaling with n, that's good, right? If you're not getting a much larger norm, or the graph is looking significantly different, you're probably in good shape. Okay, great. So let's talk a little bit about the operation count. So I'm going to do it in the form that we just saw. So we pre-compute these so-called twiddle factors, and we can pre-compute it with a 1/2, so e to the minus pi j over n. So we won't count that in our computation. J goes from 0 up through n minus 1. So these are somehow stored in memory or whatever. And then you, to compute gamma j, we need, say, we have to multiply alpha j by 1/2. This is j goes from 0 up through n minus 1. And we also have to multiply beta j by that pre-computed twiddle factor, 1/2 e to the minus I pi j divided by n, like this. So the total is 2 times n multiplications. Like I said, we won't worry about the the additions and subtractions there. So it costs about that much. And so let's let R2n, say Rn, excuse me, Rn, denote the cost of computing. Say degree n and trig polynomial. Then I should have mentioned this algorithm of splitting into odds and evens and then recombining is called the Fast Fourier Transform. It's called the Fast Fourier Transform if you do it recursively all the way down the loop. Let's take n to be some power of 2. So the idea is you do it for the odds and evens, and you get a savings. Well, why not, when you're computing the odds, why don't you split those into alternating points and split the evens into those evens into alternating points, and so on down the line. So in that case, then we get R of n. This is equal to R of by what we just saw. This is R2. Well, this is R2 little n. But by the above arguments, this is 2 times the cost of computing Rn once plus 2n for the extra multiplications. Where we have to compute the smaller stuff. This is the little b and the little q, and it costs us 2n operations as we counted above. But then that means that so if we take R2m, this is 2 times R2m minus 1 plus 2m. We can then split this guy up. If we keep going, this is 2 times R times 2m minus 2 plus 2m minus 1 plus that 2m on the end. And adding these up all the way down, we'll get to something of the form. So this is, we'll get a 2 squared out of here and then a 2 cubed and so on. We're getting a geometric series here in the back. So putting all of those together, we'll get, excuse me, not a geometric series. We'll get 2 times 2 to the m minus 1. So maybe I should just write that out. Excuse me, getting ahead of myself there. This is 2 squared times r 2m minus 2 plus, well, it's going to be 2 times m minus 1 plus another 2m. So that's 2 of these 2 m's. If we keep going all the way down, we'll get down to 2 to the m times r, the cost of just computing Fourier coefficient just for one data point, where you just return the data point itself, right? That would be a constant trigonometric polynomial, so just at the point itself. And then these 2's will keep accumulating. How many times will they accumulate? Well, we need m steps to get down to the bottom. If we have 2 to the m together, then as we keep splitting and splitting and splitting these, we'll get something like 2 to the m. So this is something like R1, so the cost of computing one of these, which maybe we just call 1 plus m, 2 to the m. This is equal to, this is, let's just call this roughly, this is m to the 2m, roughly speaking. But that, converting, since 2 to the m is n, we get, this guy will be, little n itself will be log base 2 of n, and then this 2 to the m here will be at n. So that's where this famous n log n speed for the fast Fourier transform comes from. Maybe I'll make, whoa, sorry. One last remark. To do this in practice, if you want to go code your own Fourier solver, you see it looks pretty simple with just a short loop to take care of this. But notice that because you're going to be splitting and splitting and splitting all the way down, those loops will change size. So you'll need a loop over of size little n, but then at one level down, you'll need a loop over size n over 2, and so on. You have to keep splitting these all the way down. In that case, it's very useful to write this as a recursive algorithm. In practice, though, and it's fun to code your own and see how this thing works, I encourage you to do that. But if you want to use the Fast Fourier Transform in practice, you should really be using built-in functions because they are highly optimized in most codes all over the place. Anyway, that's one thing. Also, if you don't have something which is a power of 2, this algorithm is a little less efficient, but you can do, for instance, you can just add a bunch of zeros onto your data and then use the transform as regular, do this algorithm as regular. There are also different radix values that you can use. So instead of splitting by 2s, you can split by 3s or by 5s or whatever. And you can even have a split radix thing where you're using different powers of these things to kind of get more efficiency. But I'll leave that for you to discover on your own. So thank you very much for your time, and have fun with the